the screen, if I may, Sergio. I have to share one slide just so we can kick everything off, if you don't mind.
Okay. Okay, so I stop sharing. Okay.
Yes, please. And then, so you're okay if we record a session, right? I think that's fine with you. Yeah, excellent.
Yes, no
Thanks
problem.
for that. So before we start, I'd just like to share one quick slide there. Let's see if I can make it work. Is that working? Can you see the actual?
Yes.
Yeah. Okay.
Can see it. Yes.
Great. So maybe we start. And yeah, thanks everyone for joining us for this webinar today. It's a great pleasure that we have Sergio Galindo-Torres with us today. But before we go into the seminar, I would like to make a couple of announcements. So first of all, as you know, Anagram is a small association, but we're trying to grow. We're also trying to involve people from other disciplines. We have quite a big sort of representation from geomechanics, but we also have chemical engineers, and we're trying to involve mechanical physicists, and yeah, spread out. Whoever works in granular media is welcome to join. Now, one big announcement. So every year we organize Grain Days, which is a gathering of the members where PhD students get the opportunity to present the poster. And we also have lectures. So this year, Grain Days will be held in Newcastle in Australia, not UK. So make sure you book the correct flight. It's relatively easy to get to. So from Sydney, it's just a couple of hours on the train. We also have an airport, so you can fly to Newcastle from Melbourne, also from Adelaide, and lately also from Perth. So this year we have Itai giving a lecture. We have Gerd Schröder-Turk, who is more like in mathematics, and we have Jan, who is also present here today, and Vice President of Anagram, who will be presenting a lecture. We will be sending out some more announcements shortly, so make sure you keep an eye out and register. If you are not a member yet, I encourage you to contact Francois, who's also online, and his email address is on that slide here. He will be more than happy to take the membership fee. It's only $10 a year. All right, that's everything I wanted to say. Now I think it's time we go to our speaker. So let me introduce Sergio. So we are very honored, Sergio, that you made up some time to present at this forum. So you are currently associate professor at Westlake University in China. But before that, you were in Australia, so you were at DQ. Then I think you were in the UK for a year or two, and then from there you moved to China, which now I think is your final destination. So your background is very much computational modeling. So you are the lead developer of Maxis, which is open source computational code that can deal with any sort of methods, in particular as well the discrete element and the lattice Boltzmann method. And I think that's what you are going to talk about today. It's some sort of insights from discrete element lattice Boltzmann simulations. Over to you, Sergio. Thank you.
Okay, thank you, Klaus. Let me know if somehow my voice is falling down So I
Yep.
move towards the screen. Okay, so thanks for that nice introduction. Yes, indeed, that's what I'm working on here in China. I wanted to introduce a bit the lab that I'm heading. So it's the multi-scale, multi-physics modeling lab. So basically what we do is we actually tackle problems coming from engineering areas such as mining, environmental, and civil engineering. And from the observations that we have from those areas, from field observations or problems that they want to tackle, we try to devise models for it, starting from physical experiments that we can run in our lab, and then we do the pod scale fundamental simulation models that we develop sometimes. And sometimes we have to include multiple physical layers. DM is a big part of it, but also fluid dynamics. And then from the data we get from simulations and experiments, we aim to derive upscaling formulas. So that's the multi-scale modeling approach, which many of us do nowadays. Uh, Also, we're following the trend that is very popular now that we want the models to be physically sound and that the number of parameters is reduced, especially the number of fitting parameters. Because if you have lots of fitting parameters, then you can fit anything. So the idea is that at least the parameters are fundamental. Fundamental in this case, I mean that they have a physical meaning, which means they can be determined independently, not from the data you have, but from another experiment. Okay, from the computational part, we do a lot of developments as well, and that's a part that I will always keep doing. We work with molecular dynamics, we work with DM, LBN simulations, such as in this slide here. We have algorithms for grain shape. For instance, in this case, this general shape particles settling in fluid. We have flexible bodies. For this, we use material point method, interacting with turbulent fluids, lattice Boltzmann. We also have flow simulations for environmental sciences, where we consider, for instance, pollutant transport. Lately, I'm working a lot in bubbles. That's not what I'm going to present today, but it's kind of a granular material on steroids. It has all the features of granular materials plus more, because bubbles can combine, merge, and then split, and then can nucleate. They can appear from nowhere. But anyway, focusing now on what I'm going to present. I'm going to present three different problems of flow of granular materials. And for each one of these three different problems, we derive like a fundamental model to describe it. The problem is that we have three different models as well. So there is like an unifying trend between them, but still they're not fully unified. So in my opinion, there is a lot of research that can be done still on these problems. This is definitely not the end. So the first problem that I want to show is the collapse of dry granular columns. So this started like something like 15 years ago. There was a seminal paper by Herbert Hopper and Louvre where they actually studied this collapse of granular columns as a model for landslides. So the experiment is very simple. They have a granular column with a given height, and then they let it just fall down, collapse. And then they measure the deposition, basically how much distance they reach in the horizontal direction. Then when they plot the difference between that distance and the initial distance, the initial radius over the radius, as a function of the aspect ratio, the initial height over the initial radius, they saw two different trends when you plot this in a logarithmic scale. They saw a linear trend at the beginning, and then a trend that is more like proportional to a square root of this variable, with a clear inflection point. There was like a clear transition between the two ends. So Herbert Hopper, the co-author of this paper, he came to Westlake and proposed this problem to us to see if we could gain some insight from simulations. So we proceed to the simulations. We have a DM code that is able to do general shapes. In this case, spheres are obviously not good because spheres will just keep rolling forever. So you will not have like a clear deposition. So we choose cubes or Voronoi polyhedra. For the validation, we use cubes. So the good thing about DM is that the number of parameters is small. At the end, if you take the DM particles to be rigid enough, then you can ignore that parameter. And the only thing that matters is the interparticle friction. And the interparticle friction is something that you can measure independently with another experiment. And in this case, the experiment we choose was just simply a slope until it starts moving. So that's how we determine the interparticle friction between the wooden cubes. So we did the simulation and the experiment with no fitting parameters, and then we have a fairly good match. Again, we see in logarithmic scale an inflection point from the linear behavior to the nonlinear behavior, more or less at the same point. So very good. So now we have validated the simulations. We can start producing data with them. And we did so. So we did many columns with many heights. And what we notice is that for shallow columns that are very short, the deposition is like a conical deposition. So these blue particles here are actually the ones at the top initially. So the ones at the top end up at the end of the column, at the end of the deposition collapse, at the deposition profile, here and here, when the column is short. But as you increase the column height, something happens. There is suddenly a change, like an hydraulic jump. Oh, sorry. And the particles that were at the top push the particles that were at the bottom. And now the ones at the top, they don't end at the end of the deposition profile, but at the middle. Furthermore, there is like a hole in the middle here. So it becomes like an hydraulic jump or a circulation profile during the deposition process. So something changed. The rheology of this deposition changed. Somehow the inertial effects are more important than the frictional effects. The friction is not doing such a good job in dissipating energy at this high for these high columns. All right. So with that idea, we propose a number. We propose like a ratio between inertial stresses and frictional stresses, with some arguments for both of them. And at the end, when you plot the ratio between, when you derive the ratio between these two stresses, you get an effective aspect ratio. But now the friction coefficient appears here. Oh, sorry. And it turns out that if we use this effective aspect ratio, all the data that we had before from the simulations, changing the interparticle friction coefficient, collapse into a single universal curve with a single inflection point. So this number, which is, you could think that it's kind of a Reynolds number, determines where the inertial flow is more important than the frictional dissipation, when it's going to win. And this inflection point seems to be precisely the point where that changes. So the analogy could be like the Reynolds number, where you have a Reynolds number where you start having vortex shading or even turbulence. So it's a similar principle. Okay, so just as in turbulence, this could be understood as a phase transition or a bifurcation. Suddenly something changes. There is a change in the dynamical system. And we borrow then the ideas from physics coming from phase transitions that tell us that if this is a phase transition, then if we increase the size of these columns in both initial radius, the width and the height, then they should scale in a formula such as this one. This formula may seem ugly, but actually it has a physical meaning. It says that there is a phase transition around a critical point. If we choose the order or the control parameter to be this effective aspect ratio, then this effective aspect ratio has a critical point after which the whole deposition profile will change. And then the size is, we measure it as initial radius over the particle size. This gives you the scaling, how it will change as you change the size of the column. So again, we did many simulations with different sizes. Yeah, the behavior is pretty much the same, but the curves are very different. But once we implement this scaling formula, we have a universal curve, meaning that indeed this seems to be a phase transition. But furthermore, I have to accept that there is fitting here. There is this exponent lambda that we did fit, but surprisingly, this other exponent nu, which appeared here, has the value that is theoretically accepted for phase transitions of this kind, which should be 1.33. So there is only one parameter that we fit, and nonetheless, we get this universal behavior. So in this seems to be a phase transition, but still more work is needed. And for the ones of you that are a bit familiar with phase transitions, usually you have a correlation length. What is a correlation length? Correlation length is how much my state is correlated with the state up to that correlation length. In this case, the state we determined was the falling distance. So we use a correlation function just as this one. If it is indeed a phase transition, then the correlation will fall like an exponential with the distance. And the characteristic length of that exponential is what we call the correlation length, this chi here. We actually did that. We measured the correlation by the falling distance, delta set, how much this falls, and a neighbor falls the same distance. And in this, that correlation distance follows a power law, which is another characteristic of second order phase transitions. It's a power law of this difference between the effective aspect ratio and the critical one. So at the end, what we conclude is that there seems to be enough evidence to say that this is a phase transition. And we published this paper a few years ago, and here is the reference. But as you will see, this is not the end of the history of granular column collapses. Anyway, I will continue with the second problem, which is suspension rheology. And in this case, I will focus in isochoric conditions, so volume constant conditions. All right, so rheology has been of research interest in the last few years, and there is a seminal paper by Boyer in Physical Review Letters almost 15 years ago now, where they determined that, for instance, a quantity like the friction coefficient of the suspension is a single function of a number that is called the viscous number, which I define here. But they did experiments with very viscous fluids. They combined glycerin and water. And as I will show you in the third problem, that actually will not be the case for less viscous fluids. But still, it was like a significant breakthrough, discovering that there is a number that describes the rheology of the suspension. And in the rheology of suspensions, we have a rich amount of phenomena going from Newtonian fluids to fluids that actually suffer shear thickening or shear thinning. Yeah. So at the end, everything goes into the grain scale physics. What determines which kind of rheology you will have? By rheology, I mean what's the form for the viscosity as a function of the shear rate. Yes. Okay, so again, we use DEM. In this case, we use spheres because the experiments that we carry out were also with the spheres. We couple it with lattice Boltzmann, and this is the standard lattice Boltzmann coupling. One criticism that we always get from the papers, and is repeated ad infinitum, is that we don't include lubrication forces. So we decided to test that, the lack of that. And well, first, we tried different schemes for the interaction between the lattice Boltzmann fluid and the DEM particle. If you're familiar with that, there are different schemes like immersed boundary, immersed bounce back, or boundary layer, no, not boundary layer, boundary. Well, I don't remember right now the name, but there is that one. And then there is a method that is called the gamma method, which is basically exemplifying this formula here that changes the fundamental lattice Boltzmann equation. Okay, so what we discovered is that we took some experiments that they're in the literature in this paper by Harada in 2001. And the experiments are basically a sphere falling into a plate. And the idea is that it will suffer what is called the lubrication force, which is a force that the particle will experience as it displaces the fluid separating both bodies. So experiments are here in triangles, yes. And in this simulation, for instance, the sphere is separated four lattice Boltzmann cells from the bottom. And we discovered that with the traditional method, blue one, actually we underscore the velocity as a function of that distance. Sorry, this is the distance here in the horizontal axis. But then with a correction on this fundamental equation, we actually got a better match. And this correction is just LADA, which is kind of a discrete. If you are interested, I can explain this further later on. But by modifying how you calculate this weight, basically you have a better match. So there is no need for lubrication forces. Apparently, lattice Boltzmann is able to capture, even though the interaction is just a few cells of lattice Boltzmann, you're not really resolving all the fluid physics in those four cells. Nonetheless, lattice Boltzmann seems to capture the main effect of the lubrication force. We also compare this with existing experimental data coming from rheometers. So here is the relative viscosity as a function of the Stokes number. The experimental data is green to yellow, where our simulations are blue to magenta. And in this case, we have no lubrication, and there is no real difference, especially for high Stokes numbers. There is a bit of difference for low Stokes numbers, but not much for high Stokes number. And the result is, well, fairly close. Well, this is logarithmic scale, so you could argue that for low Stokes numbers, it's not matching quite well. But for large Stokes numbers, seems to be fairly close. So it seems that lubrication forces are appropriately captured by the lattice Boltzmann, even with this coarse grid approach. Okay, so with that out of the way, we proceed to do simulations in a shear box, in a rheometer. So this is our rheometer. It has periodic boundary conditions. And the idea is to reach a state where when you have like a steady state. Again, it's constant volume, so the top lid will not move vertically, will just move horizontally. These are the parameters of the simulation. We wait until we get a linear velocity profile. That's a sign of a steady state in this simple shear system. We have an homogeneous volume fraction. So more or less you have a uniform density of solid particles across the height. And of course, we also can plot the shear stress or the relative viscosity. The relative viscosity is the viscosity that you measure over the viscosity of the fluid. And again, you need to wait until it reaches a steady state. Yes, and that's the one you measure. Okay, and then what we observed was that for different values of the volume packing fraction, which are shown here in this color map, you have different behaviors. Like for instance, for very low volume fractions, the blue one, which is the lowest, the smallest, very few particles, the shear stress measured at the lid as a function of the shear strain is pretty much a linear relation, showing that it's a Newtonian fluid. So you can define a viscosity. The viscosity does increase as you increase the volume fraction, but it's still linear. Whereas when you have high volume fractions, that linear behavior disappears and it becomes highly non-Newtonian. And actually, it seems to have like a threshold here. This is the Hockley-Bingham fluid. I don't remember right now the name, but it's one typical behavior of non-Newtonian fluids. Uh, the same for if you measure the relative viscosity, is even clearer. Indeed, it seems to be constant for low volume packings, like the blue one here, but it seems to suffer shear thinning. The viscosity decreases with the shear rate for high volume packings. Furthermore, we measure the cluster number, so the maximum number of particles clumped together, basically. For high volume packings, basically there is no difference. All of them are clumped. All of them are in contact. Yes, but then for low volume packing, it seems to depend on the shear rate, how much they clump together. So when the shearing is slow, they're actually like disconnected particles. But as you increase the shearing, then you start having these clusters. This will become more important later on. We actually compare with Boyer. Boyer did this is the seminal paper that I mentioned a few slides ago. And Boyer did actually constant pressure experiments. So this is different. This is constant volume experiments. But nonetheless, and here are the curves, for instance, for the friction coefficient. Nonetheless, there is a bit of a similarity, especially towards the low volume packing fractions, the blue ones, when the particles are few. Then it seems to be attracted to the main curve by Boyer. But as you go lower in the viscous number, then you start seeing divergent curves, as you can see here. Also, the volume packing doesn't match, and it should not, because that's what we're controlling. Yeah, but it seems that it also follows kind of the trend of Boyer's results. But in this case, for isochoric conditions, definitely we cannot use the results that Boyer obtained. Well, it's interesting that they're similar anyway, that it seems to follow similar trends. Okay, so we plotted like this. We plotted the inverse relative viscosity against the shear rate. And we saw this kind of division between the two regimes. So this is the Newtonian regime, you could call it like that, yeah, where the relative viscosity doesn't change that much. And this is the highly non-Newtonian regime, where actually the relative viscosity changes a lot. Yes. Then what we did was to find like a middle point, yes, which is what is known as the jamming volume packing, to see if we could somehow split the curves into two universal curves. And actually, we found like a power law relation for the relative viscosity and the shear stress. And once you introduce that critical difference on the volume packing as a power law, dividing the two quantities, the shear stress and the relative viscosity, then you start having universal curves. Now, what is the difference here? The difference here is that we change the stiffness of the particles. So each one of these universal curves is for one stiffness. But once you take, now the relative viscosity is dimensionless, but the shear stress still has dimensions of pressure. But once you divide that by the stiffness, we use the linear dashpot. So this is a classical stiffness for the dm particle. This is the stiffness over the size of the particle. Once you take the stiffness into account, then you have a dimensionless number here. Yes, and a dimensionless number here. You divide that by this critical power law between the volume packing and the critical volume packing, where you have the transition, and then you have a universal curve like this. Then this bluish greenish regime is the Newtonian regime, and this reddish regime is the non-Newtonian regime, and you have two universal relations for all the data we obtain, which are showcased here. Now, we don't know what are these two functions, f and g, but at least we know that definitely they're functions of this fundamental variable, and you have two curves, depending on which side of the volume fractions you are in, if you are higher than the critical volume fraction or lower than the critical volume fraction. So this already gives you an insight of how to proceed, how to find the relative viscosity. So this is something that could be programmed in in a code like SPH, NPM, FEM, yeah, if you need the relative viscosity for this suspension. So we found this kind of universal relation, which is good. They're similar in form to the one of granular column collapses, dry granular column collapses, because the physics is kind of similar. There's a transition point, a phase transition between two very different behaviors. And in this phase transition, then, we know that these kind of formulas, as ugly as they apply. I have to say, though, that there is fitting here. These two exponents are obtained by fitting. All right. We compare with experiments. So we did these experiments in this rheometer. We use this kind of PMMA spheres. We try to match as much as possible experiments and simulations. And indeed, even in the experiment, we see the same behavior. We see exactly the same transition point. The value that we obtain from the experiment is different. We argue that it's because of the different stiffness between the particles, because in the end we use softer particles than in the real experiment. Yes, but the relations are pretty much the same. Okay, so at least this was like a qualitative validation of the theory we developed. And interestingly, and this is the paper we publish, it seems that this is a percolating problem, because if we actually plot the number of maximum particles, the maximum number of particles in a cluster, in this inset here is against the shear rate. But if we plot that against the viscous number, then it's also a universal curve like this. And if you're familiar with percolation, this is the classic percolative ratio, where you have low percolation for some ordered parameter, and then you have full percolation when you change it after a critical point. And indeed, if you plot the force change in this, it can be seen that for low volume packings, so towards the magenta pinkish area here, you have very few force change, so just clumps of particles, 2-3 particles together. But as you increase the volume packing, of course, you will have a fully granular skeleton with well-developed force change going from one end of the rheometer to the other. And that seems to be the transition between the Newtonian fluid rheology and the non-Newtonian one. So we are actually exploring this right now. We're conducting research right now on this to see if that will make the transition between Newtonian fluid and granular flow. So in Newtonian fluid, you have viscosity, the shear stress will be viscosity times the shear rate, whereas in granular flow, the shear stress will be friction coefficient times pressure. So there is a transition there between the two. And we think that the key thing is the percolation of the grains from one end of the rheometer to the other, from one boundary to the other. Okay. All right, and now a bit of less simulations, more analytics. This is the last example I'm going to show. This is an example also on suspension rheology, but now in isobaric conditions. So in this, we're borrowing again the idea from Boyer. We're letting the top lid going up and down with constant pressure. Sadly, the behavior then is different. In that case, the volume fraction, actually, you need to let it develop naturally. You don't impose it anymore, but it will develop naturally, like in the concept of critical state of soil mechanics. Basically, you will reach eventually like a critical volume packing or a critical void ratio. In this case, we're going to actually consider fluids with different viscosities as well. So this is of course a problem that has been studied before. There is a very famous paper in Journal of Fluid Mechanics. It's a review paper. If you are interested in this problem, I really recommend you reading this paper. It's very clear and it exemplifies all these phenomena very nicely. Okay, so basically we have all kinds of of void ratios and then different rheology behaviors, like in the problem before. There is, for instance, jamming, where you have a high volume packing, or basically a dilute regime where it's mostly Newtonian. It also depends on the viscosity of the fluid. For high viscous fluids, we have the viscous number, which is the one that I described before. Whereas for low viscosity fluids or dry cases, we have the well-known inertial number that I think everyone working in granular materials is familiar with. So we have these two extremes. We have inertial number for very dry flows or flows on air, which is very low viscosity. And then we have the viscous number for things like glycerin with water that are highly viscous. So what's in between? That's the question that we had as well. The numbers are actually quite different, but also quite similar. They're both proportional to the shear rate. One has the particle size, the other has the fluid viscosity. Both have the pressure, but the pressure here appears like a square root. Yes. So why they're so different? Why the rheology changes from one governed by this number to one governed by this number? So in this research, which is much more analytical with no simulations, we tried to answer that question. And we did it by a very simple high school mathematics level model of just taking all these shear blocks in isochoric conditions with a given pressure, yes, and reduce it to just three particles here, okay? So these three particles, as you shear, the particle at the top will move to the right and will tend to follow to the hole here, a distance delta, okay? But if it is fast enough, if you have a high shear rate, then it will just fly to the next particle and it will not fall down. That's the principle of these numbers, basically. This is the argument that you use to deduce these numbers. So the idea is to determine this distance delta. It is in this three-particle problem in 2D, it's very easy to determine the volume packing. Yes. And once you determine that volume packing or the critical one is the closest packing. In this case, this hexagonal or triangular packing. If you do that, then you will find that the volume packing is actually a function of how much the particle falls, delta, over the particle size. So it's a function of that. So in a real case, in 3D, with different particle sizes, this formula will not apply. But still, we can say that is a function between these two length scales. It's a length scale ratio. And we follow that principle. Maybe the other quantities are also a function of this length scale ratio. For instance, in this simple model, we calculate the friction coefficient. So in this simple model, you can do the force diagram, yes, where the interparticle friction coefficient appears here. And also Stokes, you assume a Stokes flow, so you have a Stokes velocity dependent force here. And then, for instance, in the vertical direction, you have the pressure of the fluid pushing down. This is the pressure of the lid, of the top lid, and you have the shear stress in the other component of the fluid. Then, actually, you also determine what is the value for this normal velocity, which appears in this Stokes law here. And for that, actually, you solve the equation of motion of a particle falling down by a body force or by a pressure force into a viscous fluid. Now, the difference we did here is that in the typical case for the two numbers, the inertial number and the viscous number, we assume for the inertial number, you assume free falling of this particle. So the distance grows with the time square. Whereas for the viscous number, you assume the Stokes flow. So the distance grows linearly with the time. So these are the two extremes, precisely. That's why one number depends on the square root and one number depends linearly with the pressure. But if you actually solve the equation for any time, so it's neither linear with time or quadratic with time, but in the middle, then you have an ugly equation, yes, but still you can solve it. And then you determine that mu is a function also on that length scale ratio. And this length scale ratio can be determined analytically. And this length scale ratio is actually the new dimensionless number that describes what is in between, which is the one I present here. Again, you can actually derive it analytically. Analytically. The expression is this one. J and I are the viscous number and the inertial number. It's ugly, but it's an analytical result. Yes. And actually, it's answer a question that is prevalent in rheology, which is in which state you can determine your shear box is in the viscous extreme or in the inertial extreme. And actually, what you find is that they're in both. It's just that there is a weight here, this lambda, that is a function of the Stokes number. Yes, and that way is given analytically by this expression. And once you have that, then we took the experimental results and actually we took DM results from other measurements, dry, with air, with water, with different viscosities going from 11 centipoisel to 3000 centipoisel. And then we took all this data from the literature. We didn't do simulations. We didn't do experiments. We just took the data. And then the volume packing becomes a universal curve as a function of this G number. Yes. So that was amazing. That was something that made us very happy. And the paper was published as a letter in Physical Review Fluids. Here is the reference there. But still, I have shown two models with transitions, potential phase transitions, and then we have a number that seems to be meaningful for the rheology of these suspensions, or even in the dry cases as well, because it transforms into the viscous number, or it transforms into the inertial number, depending on the Stokes number. But still, we don't have a connection still with between all these different models for all these different cases. There is no unifying theoretical framework for this kind of rheologies. So that's how I will end my presentation, with a bit of frustration because we still don't have such a framework. So we have studied a broad range of flow and granular materials, dry collapses, suspensions. We have some key features that are common, transition points. It seems that the transition is always between inertial flow and some flows where the resistant stresses start playing a role, viscosity or friction. Yes. But still we lack that unifying description on these processes, and we're actively working on that. So I hope I also pique your interest on this problem, which is very nice, very beautiful, and of course with high applications, no? Because flow granular materials, well, we know that it has many applications in mining engineering and civil engineering. Okay, so with this, I want to also acknowledge the contributions from my team, which I showcase here. We're always looking for people. So if you are interested in spending some time in Hangzhou, China, please reach out. We have this new university, Westlake University, which has very good support. So right now will be a good time to join. And I will also want to acknowledge my collaborators. You all know Alexander, of course, because he's very prominent professor in Australia. And Herbert Hopper was the one who introduced us to the problem of granular column collapses. And Kimberly was the one who actually proposed to us the suspension problems that we tackled during these years. So thank you very much. That is there.
Thank you. Excellent. Thank you so much for your insightful talk, Sergio. Lots of interesting slides and lots of equations. I can see you have been very busy back in China. And as you said, it's a good opportunity to see what's done in this space from theory, analytics, and also the modeling perspective. Look, I'm sure there are some questions from the audience, so I'm happy to open up for questions. Feel free to just speak up. I think we are a small enough audience that we can just speak. So unmute yourself and ask a question.
Sergio, thank you for a very interesting, very inspiring talk. You taught us not just about what they can do and what's still a challenge. I have a couple of questions. Can you hear me? Because I lost my voice. Sorry.
I can hear you, Chao. Yes.
Yeah. Couple of questions, not quite related, to some extent relate to your talk, but I have been following your work. When we use lattice Boltzmann DM to simulate unsaturated soils, I think you published a paper, not as the first author, but with someone in the middle. You try to simulate SWCC. How far can we go in that? Because you mentioned in your talk viscosity. You can simulate fluid with different viscosity. The real challenge is in one soil, we have one fluid, water, the viscosity can change. Depends on the location of the fluid. If it's very close to the soil particle, the viscosity increases. You call it film water. For example, in your paper, you showed the suction is different in the film water and in the capillary water. In the future, can we simulate one fluid in one soil, but with different viscosities? Depends on the distance to the soil particles.
You have touched a very emotional, very frustrating part of my research. I have to say that I have tried for a number of years now to really have this super DM LBM for unsaturated soils. Sadly, it has been very challenging and I'm very frustrated with the results so far. Because I have a problem there that I have not been able to solve satisfactorily, which is mass conservation. Lattice Boltzmann, because it's a grid-based method, when you combine it with DM, which is meshless, you have this problem of the invasion of one DM particle into a cell. The problem is that when you use a explicit solver, no matter how slowly you do, there is always some fluid that will get into the particle. In full saturated conditions, like the ones in these simulations, that doesn't matter because you occupy the cell, but you empty the other cell, which also has fluid. So the total mass is conserved. You have a constant density of fluid everywhere. But then when you have density gradients, such as in the case of unsaturated soils, then this becomes an issue. So yeah, I did publish some papers on that, but I'm fully aware of this problem and I haven't been able to solve it to my satisfaction, let's say. Because yeah, I want to have the ultimate tool. And as I showed you here in the beginning, I'm working with bubbles actively actually. And now we have models that are able to capture physics like Henry's law, dissolution, nucleation of bubbles. So if we combine that with DM, we will have the ultimate simulation tool for this kind of problems. But right now, because of this mass conservation problem, I still not feel confident of doing that. So that's a key thing. If we solve that, let's hope that soon. But I'm becoming pessimistic with the passing years. Then of course we can tackle the problems you're proposing because we will have local different local density gradients and hence local viscosity gradients. And then we can study rheology, even rheology for these unsaturated conditions. with the formation of the solid matrix. We could also, for instance, fracking, because DM for fracking is kind of established. So fracking with multi-phase flows, fracking with a combination of methane gas and water, and the full deformation of the solid matrix. So it will be like really, really a very powerful tool to do these problems. An alternative, which I think Jiang did, was NPM. Or another meshless method for the fluid. Then, of course, if you use a meshless method or a particle-based method, you have mass conservation for sure, because the particles, you can always expel them out of the DM particle. But then the advantage of lattice Boltzmann is all these other physics that it captures, the nucleation, dissolution, Henry's law, things like that. So yeah, that's pretty much what I'm aiming for, but it's very challenging.
Yeah, I agree with you. I think NPM is a continuing method because we want to understand the physics at particle level using the DEM LBM simulation. Anyway, I have a more fundamental question, which I have been asking around for the last 10 years or so. You know, when we talk about DEM, in our DEM, the particle size variation usually is 1 order of magnitude, which means the largest particle is 10 times the smallest particle. In such a soil, we don't need unsaturated soil mechanics. We don't have internal erosion. We don't have mud pumping. This is a very good soil because it's a uniform soil. In a real soil, we at least have 3 orders of magnitude, which means the largest particle is 3 times, 1,000th times the smallest particle. If we want to simulate a triaxial soil sample with 3 magnitudes of, with the largest particle 1,000th times the smallest particle, we need about 1 trillion particles. How do we get around this? This is not a computational capacity problem. This is a computational methods problem. So we have to find a way to solve it. Otherwise, it's no meaning to talk about unsaturated soils if it's pure sand. There's no suction, nothing. It's a very good material. There's no internal erosion either. It's only when we mix a little bit of clay in sand, we get the problem. We need unsaturated soils. Yeah. If it's clean, uniform sand, we don't need unsaturated soils. There's only 2 states, dry and fully saturated. So if we want to include a little bit mixture across different sizes, make unsaturated soils more meaningful, make our simulation more meaningful, we can't just deal with soils with one order of magnitude difference in the size. What's your opinion on this?
I totally agree with you. That's another thing that frustrates me about this DM with unsaturated conditions. That even if we produce it to my satisfaction, we will only be able to simulate REVs in small sections of the clay materials, but not the whole picture, not the whole interaction between these sizes. So at the end, we will have definitely an incomplete picture of the whole soil. Well, probably we will not see it in our lifetime. Nonetheless, computing power is increasing. Maybe someday we will be able to simulate trillions. Definitely, I think computing power will not be based on silicon. It will have to be based on something else because the silicon-based computing is reaching its limit. Yes. Now, for instance, here in China, they're working in photonic computing processing, kind of fiber optics, but with photonic logical gates. Maybe that's an option. I'm not quite sure. I had my hopes in quantum computers, but now I understand that quantum computer is actually just another model of computation just for some problems. But let's say that molecular dynamics with quantum computers is not really a thing. It will just be the classical algorithm. So we will still have the same problems, the neighbor searching, which is the expensive part, the force calculation. So at the end, let's wait for more computing power because the DM algorithm, I don't think is going to change much anymore. We can introduce more things. We can combine it with different methods to have multi-physics simulations. But at the end of the day, DM and at its core, Newton's laws will not change, and the computation requirements will not change. So we need more computational power.
Sergio, I don't quite agree with you. It goes back to my first question. A lot of geotechnical problems caused by the fine particles in the granular material because they can be part of the fluid, they can be part of the solid. When it's very dry, we make bricks. What's brick? Brick is because the clay in the sand is bonding it so tough. So if we can simulate local density variation or local viscosity variation, we might be able to get that. I don't think it's a computing power issue. We really have to think it's a computing methods issue because in real soil, it's not 3 orders of magnitude. It's 6 orders. To the extreme, it's 12 orders of magnitude. We will never get to that computing power. We will never. So unless we develop new computational methods in an innovative way, I don't think I will get that. But anyway, thank you for your comments.
Okay. All right. Definitely. We don't have an answer for that. Let's see.
Yeah, I think it's a really good question. But I mean, following up on this, do you think we hit the wall in terms of computational power at the moment? I mean, there are limits, right?
Well, people is impressed now with AI, no? So we have ChatGPT and all those things. If you think about it, the algorithms for AI have not changed much. We have the perceptron from the 60s, and it's pretty much the same neural network that we have right now. But what has changed is the computational power. So these companies like the one OpenAI, they have its GPU farms, millions of dollars spent on that. That's what really kicked the AI thing, in my opinion. Now, not so much the development of the algorithms, but the computational power that allows them to try many things constantly and then refine these language models. So computational power is still increasing, yes. Moore's law seems still to be on track, especially for GPU, doubling the power every 18 months. But definitely I think there are theoretical limits for silicon-based computing. So at the end, we will need another kind of computing model.
Mm-hmm. And another question, you mentioned GPU. Is your code GPU based?
Yes. Yes.
And can you do both shared memory and sort of MPI, so CPU parallel and GPU? So hybrid sort of?
No, right now. No. So sometimes we share some work with the CPU because like for instance, when you only have 10 DM particles for some simulations, we do that. Then the 10 DM particles is faster in the CPU. So actually the bottleneck, which is the communication between GPU and CPU,
yes,
actually is worth it. It's worth it in that case because the CPU is much faster. You can do that, for instance, you simulate 1 million DM particles in GPU is faster than in the CPU, yes. You simulate 2 DM particles in the GPU, it takes ages because the GPU cores are slower. It's just that you have many, but per GPU core, they're way slower. So sometimes when you have few particles, it's better to do it in the CPU. and then leave the lattice Boltzmann for the GPU, because lattice Boltzmann is like created for the GPU. But no, I have not programmed with full MPI sharing different GPUs. No, we don't have that capability right now.
Okay. I know we're running out of time, but is there any other question or burning comments?
Sergio, I have a small question about the rheology part. So I think
Yes.
your current simulations are focusing on mostly spheres. So do you consider the impact of particle shape in currently or maybe in the future?
Spheres have been complex enough for the suspension rheology.
Yes.
But now there is a paper recent, actually my student said it to me, of rheology of cubes. They did the experiments. So I think we will, and of course there is some significant changes in the behavior for the one volume equivalent sphere experiments. So we will aim to that, since we have the code for that. We have the code to simulate cubes in DM-LBM. Shape, you can always do the simulations with shape, and we have lots of shape algorithms in DM. The problem is that it becomes very difficult to model for upscaling. How do you introduce shape in these formalisms? That's always a bit the tricky part. You can always do a simulation, but how do you introduce which single number summarize what is shape, or a number of numbers? We have some shape parameters, Corey shape factor, sphericity, things like that. Are they enough? I don't know. Actually, I have no idea.
Mm. Yeah, really good question about shape. Yeah, look, I think it has been an excellent sort of conversation, and thanks again for your presentation, Sergio. It was good seeing you after all that time. And yeah, thank you so much for contributing to this webinar, and hopefully we'll be able to catch up soon again. We will make the webinar available on our website so members can have a look at it. And I'm sure if there are questions, they might be able to contact you if that's okay.
Yes, of course.
Excellent. All right. Thank you so much, everyone. And wishing you all the best.
Thank you, Sergio. Thank you, Klaus, everyone.
Yeah, thank you again so much, Sergio. All right.
Thank you. Thanks to you.
Bye.
See you, everyone. See you. Bye.
See you.